Okay, so we will start first with Sn2 reaction. And Sn2 reaction stands for substitution, nucleophilic, second order. So we've talked about all of these things last week in chapter 6, okay, just very slightly, okay, that you know what substitution is. That's an exchange of an atom. Then you know what a nucleophile is, which is the negatively charged thing. And you know what second order is, okay? Second order means when two things are involved in a transition state, okay? So those are the things that we know. But we call these Sn2 only after doing a lot of work, okay? So initially they were not called Sn2, but now we do. So how does this work? So here, let's take a halide. And if you are doing something else, okay, just drop everything else and pay attention, okay, to what I'm teaching you, because this is some of the most basic stuff that you're going to learn, and it's going to be useful for organic 1 and also for 2. All right, so if you are distracted by anything, this is a good time to just, close the door and just focus on this, okay, which is why I also did not want to miss our lecture today, because this is all very basic fundamental things. So here we have a reaction, okay? And I know you could have all predicted that, yeah, this is a substitution reaction because the chlorine is getting exchanged with the OH, all right? So first of all, I'm going to tell you what these things are called. So this one, the first one, this is called a substrate. Nomenclature is a big thing for us. You can tell, naming compound, okay, learning the right terminology. So now when we say substrate, both of us are on the same page, okay? The OH minus, which is the hydroxide, this is the nucleophile. Why? Also because it's negatively charged, right? So we talked about that in chapter 6, that nucleophiles are negatively charged. Then, of course, you have the product on the right-hand side. And the Cl minus is called the leaving group. Let me give you a shorthand that you can use. And these are common shorthand and you can use them all the time. So substrate, nucleophile, product, and Lg. And substrate, usually I write SUB, or you can write S also with it. That's up to you. But, and prod for product, P works for you. For me, it's a good idea to write the prod, okay? So that way I know it's the product. So substrate, nucleophile, product, and leaving group. We have 4 things here. Now, in this substrate, when you look at the substrate, you will see the leaving group there also. So you can mark the leaving group on either side. Okay, and the same thing goes for the nucleophile, because you can see the nucleophile here, and there is a nucleophile right here. So the product has the nucleophile, all right? And when you do reactions, okay, then you have to figure things out, like what is the nucleophile and what is the leaving group and all of those kind of things. And I know you will become comfortable, okay? But I'm just saying that you have to be able to identify these things, okay, in there. So the first thing is terminology. Now let's talk about the reaction mechanism, because if you have this kind of a reaction, you know this reaction works. You've gone to the lab, you've done this reaction, you get the product. So now what we have to do as chemists is to figure out how these reactions are working. What does it mean by how it's working? It means, is the Cl bond breaking first? Okay, so this bond right here between carbon and chlorine, does that break first? Okay, or how is it that the hydroxide will come and change, from chlorine to hydroxide on this carbon? Okay, so this is a question. So is Cl leaving first, or is hydroxide attacking first? What is going on, okay, in this mechanism? That is why we call this like a mechanism, and where you have to study how the reaction works, okay? All right, so the way it works, it turns out, when you study the order of reaction then, because what you do is you study the kinetics, okay, of this reaction. So the kinetics will help you determine what the transition state is. And if you remember the transition state, we talked about that if you have something like this, right here is the transition state, okay? And the transition state can have one thing or two things in there. That depends on the order of reaction. So if the order of reaction is one, only one thing is involved in the transition state. If the order of reaction is two, then two things are involved, okay? Bimolecular, remember? So I said unimolecular if you have one molecule, bimolecular if you have two molecules, okay, in there. So it turns out that when we study the kinetics of this reaction, the rate equation turns out to be this. So I'm not writing 1 and 1 because if you're writing that in the rate equation, it means it is automatically 1. Okay, sometimes it feels good to write the 1 and 1, but honestly speaking, you don't need it. Okay, because the rate equation, you will not write a chemical in the rate equation if it was 0 order. Okay, so technically speaking, that's, you don't write that if anything is 0 order. So in this case, it turns out that the substrate and the nucleophile, they're both needed in the transition state. Okay, so this transition state that we have here, that is a bimolecular transition state because the rate is dependent on both. And you remember how we do this is you keep the substrate constant and you change the concentration of the nucleophile. If the rate changes, if the rate doubles, then you have a first order according to hydroxide. Then you keep the hydroxide constant and you double the concentration of the substrate. If the reaction rate doubles, then of course it is first order according to the substrate also. So the same thing that you did in Gen Chem is exactly what we do here in order to figure out the order of reaction. So now we're not doing the math part, we're just writing the rate equation. So now that we know that, okay, we need both of these things, right? So this is bimolecular. We need the substrate also, and we need the nucleophile also in order to write the mechanism of this reaction. So it's a bimolecular reaction. Okay, fine. How does it work then? So here is the chlorine. On this carbon, you also have the hydrogens. And you can see also, I don't have to be, picky to show you or kind of point it out to you, but you can tell that the reaction is happening on this carbon, right? On the carbon where the chlorine is, that's where all the action is. Okay, and why is the action there? Is because this is the electrophile. If you have a nucleophile, you have to have an electrophile. So remember, the electrophile is where the positive is. Why is this carbon positive? It's because this bond is polar. I'm going to erase all of this in a second, okay? So this is delta negative, and this carbon is delta positive. So I had you write the delta positive and negative so you understand what is the electrophile, okay, in this case. So when you have any kind of a halide, that halide causes a polar bond, because that halide is more electronegative. So halide gets the delta negative. That carbon that it is attached to gets the delta positive. Okay, I'm going to have to erase this because I need to draw some arrows. But hopefully you all understand what the electrophile is now. Okay, over here. Oops, I think I got one more carbon. There we go. All right, 3 carbons, and then you have these 2 hydrogens, okay? So now what we are saying is that both the molecules are involved in the transition state. So learn to write on the arrow, okay? I'm going to explain all of this also to you. So write on the arrow the hydroxide. So hydroxide comes in, and if you want, change the color of your pen. This is attacking this carbon right here. So if hydroxide is attacking that carbon, this is just the start of the reaction, okay? So what happens at the transition state now, because hydroxide is now forming a bond, right? So hydroxide is trying to form a bond The hydrogens cannot move anywhere. Remember, the carbon-hydrogen bond is not the polar bond. The polar bond is between carbon and chlorine. And chlorine is also our leaving group. So which means that the bond that needs to break is the one with the chlorine. So I have dotted lines for that. And what it really shows is that the hydroxide is coming in and the chlorine is leaving. I'm going to change something, okay? I'm so sorry. I'm going to have to change something here because the arrow, I need to draw it in a different way. I hope you have pencils. Here. Okay. Because this hydroxide actually attacks from this side, from the back side. Okay, so I'm going to have to change the H also over here. Actually, I don't have, well, here, I have to change this bond. I'll explain that to you in just a second. Keeps telling me that my internet is unstable. Okay, let me highlight what I did here, okay? So the hydroxide is attacking from behind. And now the hydroxide is behind where the leaving group is. They're on opposite sides. And we're going to be talking about this later on, about some of the angles, but they have to be on the opposite side of each other. So let me explain this, okay? Why I had to change the arrow and why I changed the arrow is because think of this. I don't know how to write. Let me try and write this, okay, in a tetrahedral way here. So this is the carbon. Remember, this is how it is. So let's say chlorine is over here. This is hydrogen, hydrogen, and the ethyl group is here, right? Ethyl group is this one. So this is kind of what we have. Now I want you to think of this as a tetrahedral only, okay? Don't think of it as in a 2-dimension. I want you to think in 3 dimensions, okay? So again, you can put your 3 fingers down if you needed to. So, but that's kind of the tetrahedral we are talking about. So when the hydroxide comes in, when the OH minus comes in, it cannot attack from here because here you have what is called steric hindrance. Steric hindrance we have talked about before. Steric hindrance is when you have spatial problems, right? When there's not enough room for atoms or molecules. So there is steric hindrance on the top, which means it has to come from the bottom. There is no way that it can come from the top. So the bottom is the only place where it can come from. So it has to come from the opposite side. This is called a backside attack. It sounds like we are in war, but apparently in the world, there is a war somewhere. It's very sad. So it's a backside attack because you can't have the OH minus coming from the same side as the chloride. If you have a tetrahedral, you can try that out, okay? So just think of it like an umbrella also, okay? In some ways, if you want to. I guess that's probably not good yet, no, because umbrella is facing on one side. Anyhow, okay. So that's the backside attack. So then you get this kind of an intermediate. Now what I've drawn over here, the highlighted one, in the square brackets. First of all, it's in the square bracket because it's a transition state. And I'm going to also write this on it, this symbol with a line and an equal on it, that stands for transition state. So the square brackets and that symbol indicate that this is the transition state. I'm taking way too long on this, so I'm going to just finish this off now. So now the chlorine is going to break off. And you will have the OH, the H's are there, and the Cl is gone. That's the leaving group now. So the main thing that I want to show you here is the fact that in the transition state, you have both the hydroxide as well as the chloride. So the leaving group and the nucleophile, you know, they're both there. on the substrate. And that is why this is a second order reaction, okay? But the substitution is taking place, all right? And so with the substitution taking place, you just have to know whether the bond is breaking first or whether the nucleophile is attacking first. So here the nucleophile is attacking first. Now, why the nucleophile attacks, that is also something we have to talk about eventually, okay? Of course, there is the electrophile, but why is it that it can kick off the chloride, right? Because you have the hydroxide, which is negatively charged, and then you have the chloride, which is also negatively charged. So how is it that hydroxide is able to kick off the chloride? There must be some reason for it, it just can't happen just like that. So we'll talk about that. Okay, but before I go on to the next mechanism, I need to just point out one thing here, okay? And that has to do with the backside attack. So because this is a backside attack, we have to talk a little bit about stereochemistry. So for example, let's take something like this. The Cl is coming out at you, the hydrogen is going behind. So when we say there is a backside attack, so here we're going to write the mechanism without writing the transition state. So when we say there is a backside attack, it means the chlorine is coming out at you. It means that the hydroxide is coming from behind. So if it is coming from behind, so now what's going to happen in the product, the OH is behind and the hydrogen moves to the front. So what happened over here now? You went from something that was R to something that is now S. So this is called inversion of stereochemistry. This is something that happens all the time when you do an Sn2 reaction. Okay, so this is only for Sn2 that you will see an inversion of stereochemistry. And this is something we have to pay attention to now. So you start with R, you get S. If we had started with S, we will get R. Okay. Another way of looking at it is if I were to draw something that is cyclic and draw something that is like cis, for example. So if I were to take this kind of a substrate, and let me go ahead and change the nucleophile, because otherwise you'll think I only have hydroxide in my lab. But I have amide also. So NH2 minus is amide. So now with the backside attack, my final product is going to be a trans product. And then I also have the leaving group. And in case you're wondering why I'm not writing the leaving group, here, I'll write it for now. But generally we end up kind of forgetting about it sometimes, but I'll write it. So that's inversion of stereochemistry. So you start with the hydrogens being cis, and now the hydrogens are trans. Okay, so cis and trans. So that is inversion of stereochemistry, and that is a characteristic of Sn2 reaction. Now, you're writing all of this. This is all fine. Eventually, what you should do is make a table for yourself, okay? And you will see that I also in my PowerPoint have tables for you. So use that table to make your own. Don't copy mine, make your own, okay? Because it's always good to have things in your own handwriting. So this mechanism that we just talked about was Sn2 mechanism. Now I'm going to talk about Sn1 mechanism. Same thing, substitution, nucleophilic, but now the 1 means first order. First order means unimolecular. So I hope you catch this. Is look at the kind of substrate I'm using. My substrate is a little bit different now. It's not the same as what I had before for SN1, for SN2. So the product here is still a substitution product. You still have a leaving group. You will get used to my writing because now we are really getting into organic chemistry. So what I do generally is I write my nucleophiles on the arrow. I can write my nucleophile like this also. If you like, write this, that's also fine. If you write it on the arrow, that is also fine, okay? Just make sure you write it somewhere. On the arrow, we write so many things on the arrow. I'm going to show you, okay, how to write things on the arrow so that you also start getting comfortable with it, okay, because that's what organic chemists do. Okay, so this one is supposed to be a first order. What does that mean? It means that the rate is only using one thing, okay? Remember, first order is unimolecular. But what is that one thing? It turns out that that one thing is the substrate. So you can change the nucleophile as much as you want, but nothing is going to happen, okay? Which means that the rate of reaction is not going to change. In this case, in SN2, it did, right? In SN2, it was dependent on the nucleophile as well as the substrate. But here, it's only on the substrate, which means that the substrate is the only thing that is involved in the transition state. So to write this mechanism, this is what happens. So you have the chlorine, and the first step that happens in this case is the chlorine is going to go away. And you can write on the arrow minus Cl minus. So the chloride is the leaving group, and the minus tells you that it is leaving. You don't have to write the plus for hydroxide, okay? If there's nothing in front of it, means you're adding that. But when you're subtracting something, when you're removing something, then you need to rewrite the minus in front of it, okay? So the chloride is leaving, okay? So once it leaves, what do you get? You get a carbon that does not have electrons because the chlorine is leaving with its electrons. Now, if this arrow is bothering you, you can write this arrow. See, this one is pointing to chlorine. The first one that I had, this is the first one, this is the second one. The first one I had, and again, this is something that organic chemists do, we just write things going out because it's leaving with the electrons, okay? The second arrow is showing that the electrons are actually going on chlorine. The bond is still breaking. It's the same thing. Whichever arrow you prefer, you can write that. I have no preference, okay? You can either write one or two. It doesn't matter. Whatever makes you feel comfortable, okay, that you understand this, this is how you understand, that's fine. But what you end up getting is this. And now this is the transition state. And again, remember, we have to draw this. This, if you remember, is called the carbocation. So we now actually have a positive carbon, okay, in our mechanism. In SN2, we did not have that. In SN2, actually, we were trying to draw 5 bonds on carbon. One was breaking, one was making, okay? So we were trying to draw that, but here we actually have a carbocation, which means a 3 bonded carbon, okay, which is lacking electrons. So now what happens? The last step is pretty straightforward because now comes in the nucleophile. So hydroxide comes in, and now it will attack the carbocation, and you have the product. It seems simple enough, which it is, but I'm going to explain something to you. And I don't have my model set here with me, but I would like you to imagine some things, just like I was asking you to imagine the tetrahedral. And the tetrahedral to understand the backside attack, okay, in there. So in this case, you need to understand the carbocation, all right? So when you form a carbocation from a tetrahedral, okay, the tetrahedral is actually an sp3 carbon, right? That's the carbon over here, and that's why this is AX4, as we call it. The carbocation is actually AX3, okay, because now you have only 3 bonds coming out of it. So suddenly what has happened is you have changed the geometry of the molecule. You've gone from a tetrahedral to a trigonal planar, okay? So once you have a planar molecule, so think of it like a fan, okay? And a fan is flat. So now when the nucleophile comes, the nucleophile can come from below or it can come from above because it's a flat molecule. So if it's a flat molecule and a hydroxide is coming from either side, it means that the product that you end up getting is what we call a racemic mixture. And remember, racemic mixture is a mixture of R and S, equal mixture. This carbon is not chiral. Okay, by the way, yeah, in case you're wondering, I don't see any chiral carbon. No, you're right. So there is no chiral carbon here, but if there was a chiral carbon, you would get a racemic mixture, okay, in there. So if you want to write an example of that, we can do that as well. So let's say, I think this would be something like, I think I need more carbons than this there. Let's take something like this, okay? So here we have, I'm writing minus. So here, if you have this kind of, I need to just hold on 1 second. I need to make this better. Okay, so Cl is coming to the front and hydrogen is going to the back. And you have an ethyl group on one side and a propyl group on the other side. And now, if you were to do a nucleophilic attack on this, so we're taking another different nucleophile now, SH minus. So if you were to do this, you're looking at this substrate. And right now, I'm telling you what this is, but I'm going to tell you how to predict whether it's going to be Sn1 or Sn2. Right now, take my word, it's Sn1. And so in this case, what happens? You will get 2 products. Okay, so you will get the one in which the SH is coming out at you, and then you will get another one in which the SH is actually going back and the hydrogen is coming out, and you get equal mixture. And that's the racemic mixture that you end up getting. Okay, let me explain a couple more things over here. And I'll draw them in sort of a table format, okay? So you understand how this is working. Or you can make your own table. I don't know. Let's do this, okay? Because one thing I forgot to draw on the top, actually I did draw it, but I didn't really quite mean it. So I'm going to go back up to Sn2 mechanism. So right up here, and if you draw this, if you drew this out, come back to it. And I want you to look at the graph. I want you to look at this graph. Because this is the graph for Sn2 mechanism. And the graph for Sn2 mechanism just has the one transition state on it. Okay, that's it. Whether the reaction is exothermic or endothermic, I'm not going to predict that because that depends on the reaction. I am predicting only the transition state. That's all. Okay, so then Sn2 graph has just the one transition state. That's it. Okay, but when we draw the graph for Sn1, it's a little bit different. So for Sn1, you actually have 2 transition states. The first transition state is much higher in energy. And what the first transition state is formation of the carbocation. The second transition state is the attack of the nucleophile. So even just by looking at the graph, you can tell whether something is a first order or a second order. Because in the second order, you will have only one transition state because everything is happening in that one step. But in the first order reaction, things are happening over 2 or 3 steps. Okay. Sometimes it takes 3, but 2 is fine. 2 is okay. All right. So this is happening over 2 steps. So you will have 2 transition states. Okay. I will urge you to look at Klein. Klein has really very nice graphs, okay, for drawing all of these and showing you the mechanism. Okay, so look at that whenever you get a chance. Questions, anything right now before I go on?
Hi, Professor.
Mm-hmm.
Are you able to give us an example of one that would have multiple transition states, more than 2?
For 2, you would need to have 2 leaving groups.
2 leave. Okay.
Yeah. So 1 for each, right? So that's why I said, okay, let me retract that back and just say that, yeah, you get only 2. Okay, yeah. Okay, so this is your introduction. So the first table I would like you to make, and you can write that if you want somewhere, or, listen to this later on and then make your table, provided I get this video up, is you're going to write the characteristics of Sn1 and Sn2. Okay, so for example, Sn2 is second order. You have one transition state, and then you have inversion of stereochemistry. That's an important thing here. Okay, so that's why I covered it. So inversion of stereochemistry. In Sn1, you have 2 transition state, okay, because you form a carbocation. All right, in this case, or you can write that first, that forms a carbocation. There was no carbocation in Sn2. Only in Sn1, there is carbocation. So, right, you form a carbocation, you have a transition state, 2 transition state, not just one for forming carbocation, one for the attack of the nucleophile. And then lastly, the product is a racemic mixture. Okay, so all of these things here, these are what we call the intro to the reaction and just the general characteristics, okay, of the reaction. So now what we're going to do is take a little break. So let me so there are going to be 4 factors that we talk about. One is going to be substrate, of course, because that's the biggest thing in there. So there are 3 kinds of substrates. So we'll talk about them. We'll talk about the nucleophile, which is a big deal. We'll talk about the leaving group, which is also a big deal. And we'll talk about solvent. Not such a big deal, but still a big deal. Solvent has to do a little bit more with the practical aspect of what's going on, because when you get into the lab, then you have to carry out these reactions in person. And so then you have to think about the solvent. When we talk about these reactions theoretically, then not so much. Okay, so we'll start with the first one, which is the substrate. I changed my pen. Okay. So the substrate, you have 3 different kinds, as we said. I'm going to write them all. Primary, secondary, tertiary. You don't have to write exactly the same structure as I have. You just want to make sure you have a primary halide and a secondary halide and a tertiary halide. Now, in case you're wondering, first of all, why I keep taking chlorine, we will talk about the leaving groups also later on, but chlorine and bromines are really good, okay, as leaving groups. So that's why I do chlorines and bromines a lot more than any other halogen, okay, in there. So anyhow, Right now, what we are talking about is actually not the chlorine, but the nature of chlorine, which means the attachment of it. So whether it's a primary attachment, a secondary, or a tertiary attachment, okay, what kind it is. So first of all, for SN2 reactions, you need more of the primary. For SN1, you need more of the tertiary halide. Now, when you write SN2, please make sure technically the way of writing SN2 is S is capital, it's big, and then N is a subscript, and then 2 is a superscript of that. Okay, this is actually the proper way of writing SN2. Don't write SN2. Okay, this is not all on one line. Okay, so make sure your writing is good. I am trying at least to put my 2 as a superscript. Okay, so please try your bestest to at least get the numbers as a superscript. So SN2 is more primary, and then SN1 is more tertiary. But then if you're thinking, what about the secondary? Secondary can go either way. Okay, so can be SN2 or SN1, which means it depends on other things. Okay, so first of all, let's talk about the SN2 and SN1 that are pretty clear and what's going on there. Okay, so let's take SN1, and I'm just going to write these again because I don't have enough room there. So I'm just writing these again. If you have space, you can continue on. So when the leaving group goes for all of these, so minus Cl minus, minus Cl minus, the leaving group is going away. We're just making it go. Don't worry about anything, okay? As to what we are forming, nothing. Don't worry about that at all. Right now, we just want to write what is formed once the leaving group goes away. So I'm forming a carbocation. Because if the leaving group goes away, it goes away with its electrons, right? So here's the Cl going away, here's the Cl going, here is the Cl going. So each time it's taking its electrons with it, so which means you're left with carbocations. Okay, so now I want to talk a little bit about carbocations because this is a big deal. So here you have a primary carbocation, here you have a secondary carbocation, here is tertiary. So primary halides will give you primary carbocations, secondary halides will give you secondary and then tertiary. So whatever kind of substrate you have will give you that kind of a carbocation, okay? So now the question is, okay, fine, I understand this part, but why is it that an SN2 will go more this way and SN1 is going more of tertiary? So if SN1 is going more the tertiary route, and also you saw that we formed the carbocation for the SN1 reaction mechanism. So what this tells us is that this is stable. The tertiary carbocation is stable. A primary carbocation is not stable. So now let's talk a little bit about the stability. Why is it that a tertiary carbocation is stable and primary is not? And that has to do with the number of carbons around the tertiary. So around the tertiary, you have 3 carbons right here. So now I'm going to bring back a word that you learned a while back. I think we did this in chapter 3 when we did acids and bases, and that was called inductive effect. And in the inductive effect, we talked about 2 different ways the inductive effect works. One is by pulling electrons, and the other is by pushing electrons into the system. So when you pull electrons from a system, it means that whatever is pulling needs to be more electronegative. That's the only way it can pull, right? When you're pushing electrons, it has to be more electron rich. So we talked about the inductive effect as the strength of acids and strength of bases. Okay, in the strength of acids, you had electronegative groups that were pulling the electrons. In the cases of bases, they were pushing electrons into the system. Okay, what was pushing the electrons? What was pushing the electrons was the electron density. Where was the electron density coming from? It comes from lone pair of electrons. It comes from anything that has more atoms. Okay, so here, you can see that, and I'm drawing this now. You have 3 carbon atoms that are pushing electrons into the carbocation. It's trying to stabilize that carbocation, just saying to the carbocation, we are here for you, we are here for you. Okay, so it's stabilizing that carbocation. On the other hand, for the primary carbocation, there is only one carbocation saying that I'm here for you, so it doesn't have that much of cheerleading going on. On the other hand, for the tertiary carbocation, there is a lot more stability. Why? Because of inductive effect. Okay, and why because of inductive effect? Because the methyl groups, the alkyl groups, I should say in general, the alkyl groups are electron rich. How are they electron rich? Not because they have any lone pair of electrons or anything. No, they just have more electron density. That's all. So the carbons and the hydrogens, okay, those are the ones that are providing the electrons to stabilize that carbocation. Okay, that's what's happening here. So because of the inductive effect, the tertiary carbocation is much more stable. So because of that, it prefers to undergo Sn1 mechanism. Now, the primary carbocation is not very stable, so it means it will not want to undergo Sn1 mechanism. It will prefer to undergo Sn2 mechanism. Again, why? Because the primary carbocation is not stable. It doesn't want to hang out on its own. Okay, so it'll prefer to do Sn2 mechanism. Now, the tertiary carbocation, again, there is a lot of issues, okay, with the secondary carbocation because it is kind of stable because the secondary carbocation is fine. Okay, it's not unstable, but it is kind of stable. So a secondary carbocation can go either way. Okay, so what do we mean by either way? It means it depends on other factors. It means it depends on the nucleophile. It means it depends on the leaving group. It means it depends on what else is around that secondary carbocation. Okay, so there are so many things here, and that's why this chapter is a little bit challenging also, because there's nothing you can memorize. Okay, in this chapter, you just have to kind of work through a process, okay, of trying to figure out how to do this. All right, there are some things you can memorize, but some you can't. So one cation that I want to mention that is completely unstable is the CH3 plus cation. Okay, so for example, if you had CH3Cl and the Cl were to go away, then you would form a methyl cation, and this methyl cation does not form. It does not exist because it's so unstable. So if you give me a methyl cation at any point, I know that you were distracted when I was telling you this. Okay, so methyl cations can't exist. I mean, actually, even the propyl cations and all that, they don't really exist. Okay, so primary carbocations don't really exist. If they do, they undergo a little bit of what we call rearrangement, which I have to talk about another time. Okay, so not right now because today is not for that. Okay, so this is a little bit about the substrate. Okay, so now let's talk a little bit about the nucleophile. Any questions in this? Let me tell you what you have to do for me, okay, in case you're wondering what kind of questions should I expect. So the first thing, of course, is writing a reaction out, okay? So if I give you a reaction, so something like this, okay, what you have right now on the screen, if I give you this reaction, you have to write the product, which means you have to be able to figure out, do I do Sn1, do I do Sn2? And those are the factors I'm talking to you about, okay? So I'm telling you how to determine whether you're going to do an Sn1 or Sn2, because if you decide to go Sn1, then you have to give me a racemic mixture in case there is a stereocenter. If you decide to go Sn2, then you have to do inversion of stereochemistry, again, in case there is a chiral center. But otherwise, also, you have to determine whether, am I doing Sn1 or am I doing Sn2? And because I ask you, which mechanism are you following? Okay, because it's an important thing. Then I ask you to also classify primary, secondary, and tertiary, which I think you already know by now pretty well. Then I'm going to ask you for the stability of carbocations, which one is more stable. So of course, now you can tell me this, okay? This is also not all that hard for you anymore, I hope. Okay, so now let's talk a little bit about nucleophiles. And give me 1 second. I think my notes got messed up a little bit. All right. Nucleophile and leaving group are very similar because both of them are negative, okay? So if you understand one, you will understand the other one also, okay? Very well. So nucleophile, first of all. So nucleophiles are electron rich. Definitely they're electron rich because they're supposed to be nucleophiles. So they're usually negatively charged. Can't write a spelling today or ever. I'm going to use my shorthand, okay? So my shorthand is negatively charged. So they're negatively charged, which we saw that in the hydroxide and amide and all of that. They can have a lone pair of electron. So what has a lone pair of electron? That's a Lewis base. So even in chapter 6, I was having you write Lewis bases and Lewis acids because you need to be able to identify the electron-rich centers and electron-poor centers, because when you write mechanism, you need to know that. Okay, so here's the thing. When you look at a nucleophile and you're saying, oh, this is electron-rich, they're negatively charged, it kind of looks like a base, because if we're talking about Lewis bases, you know, over here, then maybe nucleophiles are bases. And you can say that generally they are. Generally, nucleophiles are bases. But you knew there was a but coming. Generally, you can translate them, okay? Which means that we've already talked about bases back in chapter 3, okay? We already talked about that. But the thing that makes nucleophile different from bases is that nucleophiles like electrophiles. What do bases like? Bases like protons, remember that, okay? So when we were defining acids and bases, acids are proton donors and bases are proton acceptors. Nucleophiles are not proton acceptors. They don't really care about a proton. Nucleophiles only care about the electrophile. Where is my positive charge? Now, that positive charge can happen to be H+, that's fine, but it doesn't care if it isn't. Okay, so nucleophiles like electrophiles. Okay, I don't think this sentence is really very good over here, the way it's written. Nucleophiles like electrophiles, or they attack electrophiles, however you want to think about it. But anyhow, so this is the slight difference between a base and a nucleophile, which means that when we say that nucleophiles are electron rich, we really mean that, okay? Because the electrophiles are electron poor. All right, so electrophiles are also looking for something that is electron rich, so it can get those electrons, okay, from them. So that's kind of how it works for a nucleophile. So which means that now we need to talk really about what makes a good nucleophile. Okay, so number one, this is something you really have to master, okay? And so I have, you know, practice for you in there. So first of all, it should be negatively charged. So I ask you to compare generally which one is a better nucleophile, okay? So when I ask you, or when you have to decide what is a better nucleophile, you look for the one that is negatively charged. For example, if you're looking at hydroxide versus water, remember hydroxide is the conjugate base of water. I'm taking something similar right now. Okay, I'm going to take something different also, but right now I'm taking something that is protonated versus not, which means conjugate acid-base pair. That's what I'm taking right now. So in this case, if you're comparing hydroxide with water, well, yeah, hydroxide is going to be a better nucleophile because it is more electron rich. Keep it simple. So similarly, if you had amide and ammonia, so again, conjugate base of ammonia, So again, amide will be better because it is negatively charged. It's more electron rich. So that's one criteria. Okay, that's if you have things that are similar, okay, in there. Then there is a size factor also, large size. The more electron density there is, the better it is. Remember that. Okay, so the large size, we've talked about this back in bases also, but here also it matters a lot. So for example, SH minus versus OH minus. In acids, we talked a little bit different, and I don't want to bring it up to confuse you, at least not today. Today, I'm just going to focus on this, okay? Maybe next week, I will talk about the difference between comparing these as conjugate bases versus comparing them as nucleophiles, okay? Because as I said, nucleophiles are like bases, but not all the time, okay? So in this case, we are taking two elements that are in the same group, oxygen and sulfur. Sulfur is bigger than oxygen, and so it's going to be a better nucleophile. Same thing goes if you had iodide versus bromide. Bromide is smaller than iodide, so iodide is a better nucleophile. And number 3, inductive effect. The self-study sheet that I have for you has all of these questions, okay? That's why I wrote to you that, we should do them by this Sunday, okay? So that you make sure that you understand all of these principles. So inductive effect we just talked about, right? Inductive effect has to do with pushing the electrons into the system. So the more electron-rich component you have, the better it is. So for example, if you were comparing CH3O minus with CH3, CH2, O minus, these are conjugate bases of alcohols. So now the CH3, CH2O minus is better. You did this for me back in acid-base chapter also. In chapter 3, if you look at it, at your assignment that you did for me, the homework, I think. So in the homework, you wrote this for me. So the more carbons you have in there, the more electron rich it will be. Okay, so if you have something like, 4 carbons here, this is a butyl group versus something like a propyl group. Okay, so butyl group obviously has more carbons in there. Now I need to explain something here. Okay, so this is kind of, again, everything is important. Whatever we're talking about today, everything is important. So when we were talking about nucleophiles, remember that nucleophiles only make a difference for Sn2. Sn1, nucleophiles are not part of the rate equation. They are not in the transition state. It's not to say that they're not important. Okay, it's just to say that their concentration is not going to affect the rate of reaction. So in Sn1, the nucleophiles are not that critical. But in Sn2, nucleophile is the key. Because if the nucleophile is not good in Sn2, your reaction is not going to happen. What do we mean by that? Which means, so let's compare hydroxide with water, right? So I said to you that hydroxide is a better nucleophile than water. But water does have lone pair of electrons. So you need hydroxide to do Sn2, but for Sn1, you can also do with water. You can use the hydroxide also, but you can also work with water, okay? Because water is still a nucleophile. And we will do that. We will write the mechanisms out, okay, for Sn1 using water also. I wrote the one with the hydroxide, but we'll write with water also. So for Sn1, your nucleophiles don't need to be so strong. So, weak nucleophiles will work. but not for SN2. Okay, for SN2, you really need to have a good nucleophile. Now, since we're talking about nucleophiles, I just want to quickly give you a little lowdown on some of these nucleophiles that we are talking about, because you're going to encounter them a lot. Okay, so like the CH3O minus here, you're going to encounter these a lot. So let me give you a little idea of what's going on here. So let's take CH3OH. Okay, how to make the conjugate base of this? This is the conjugate base of alcohol. So I removed the hydrogen. In this recording, you're going to see so many times it's telling me that my internet connection is not stable. But anyhow, so we're going from CH3OH to give you the conjugate base of that alcohol. So first of all, let's talk a little bit of nomenclature, okay? Because you're going to see these a lot, so I need to just kind of go over this quickly, okay? So we're not going to take too much time on this one. These on the right-hand side, these are called alk oxides. So alkoxides, alk and then oxide. So this is a one carbon thing. So this is a methoxide. Simple nomenclature. If you had CH3, CH2O minus, which is also C2H5O minus, either, okay, both are the same, this would be called ethoxide. Propoxide, butoxide, okay, this one, for example, that I drew before, this is called T-butoxide. So that's one thing. Nomenclature is one thing. Now, how do you actually make these alkoxides? To make these alkoxides, you need to remove the proton, right? From the alcohol, you need to get rid of this proton. So how do you get rid of that proton? Obviously, to remove a proton, you need a base. So what kind of base are we talking about here? Okay, and this is an important thing because you can't use all sorts of bases, okay? And I'm going to talk to you about this, okay? But I want you to promise me that you're going to listen to this again, because this will come up again in this semester. And if you're taking organic 2, this will come up in organic 2 because alcohols are actually in organic 2. Okay, so right now we're dealing with alcohols. So this will come up in organic 2 again. Okay, so I need a promise from you all, and I know I can't see you, but I need a promise from you on that you will listen to this again and try to understand what I'm teaching you here. Okay. So when you go from an alcohol to an alkoxide, you're treating it with a base to remove the proton, because why? Bases like the protons, right? So bases will remove the protons. So which means what we are saying is that alcohol is the acid. You treat that with the base and you get the alkoxide. So now I'm actually going to write this reaction out, okay? So you don't think that I'm messing with you. So CH3OH plus sodium hydroxide, which is a very typical kind of a base that we use. And then we're going to go ahead and write this, right? So you abstract a proton. Now you know how to do this. So you draw this arrow. So hydroxide, the O of the hydroxide is going to pick up that proton. So you have that CH3O minus, you have the counter ion, which is the sodium ion, and then you also make water. This is called sodium methoxide. Okay, if you wanted to name it, it will be called sodium methoxide, just like any kind of an ionic salt. Okay, so here is what we are forming, right? So sodium methoxide. Now, my question, okay, which I think I'm going to have to answer it myself because it's kind of hard in this kind of environment to ask questions sometimes, is this reaction favorable? Okay. So one of the things that we were talking about in acid-base chapter back then is that I want you to be able to predict whether a reaction is going to happen or not. And how were you going to predict that? You were going to predict if a reaction can happen if the products are weaker acid or weaker bases, right? That's the whole thing. So the products have to be weaker acid and weaker base. Now I want you to compare this, okay? And I'm going to give you 30 seconds to compare. So the base here is hydroxide. The base here is methoxide, okay? So considering what I just taught you just now, okay, with the bases, and you can look back into your notes if you want to, okay? I can scroll up too. So I taught you everything over here about what makes a good base, okay? And I want you to think about 30 seconds as to which one is a stronger base here. Is it hydroxide or is it methoxide? And if you feel like it, write it in the chat. The recording on, so everything I talked about is gone. So leaving group. This is the third thing. The leaving group have to be weak bases, which means they are literally the opposite thing of a nucleophile. Nucleophile needs to be either a strong base or it needs to be electron rich. The leaving group can be electron rich. I mean, it can have electrons, so it can be negative, but it can also be neutral. Actually, neutral ones are really good leaving groups, okay, because they can just go and exist on themselves, you know, so they don't really need anything else. So they have to be really weak bases. Now, I have gone over everything with you with nucleophiles. So I explained to you over here what is a good nucleophile, what is a weak nucleophile. Now, all you have to do is flip this. Okay, that's all. So I recommend that you learn your nucleophiles really well because the nucleophiles are just the opposite. So for example, if you're looking at hydroxide versus water, what is a better leaving group? Water. Okay, because hydroxide is negatively charged. All right, so that's a stronger base. So for a leaving group, you need to have something that is weaker. So that's how it works. So in a way, it's kind of easier to understand. So let me just write a couple reactions here for you. Okay, so we've been writing something like this. So I said, okay, you know, here is a, you know, propyl chloride, and you treat that with hydroxide and you end up getting substitution reaction. So what is it that we're looking at over here? So we are actually focusing on the nucleophile. We are focusing on the leaving group. So now the hydroxide and the chloride, let's look at them. So hydroxide and chloride, these are both negatively charged species, okay? So how do you tell which one is a stronger nucleophile? Because remember, nucleophile has to do with its love for the electrophile. Although hydroxide, you already know, is a good base, okay? And once you know that something is a good base, it's more than likely a very good nucleophile also, okay? But I need to justify this to you so you understand in case you have things you don't understand, okay? So the best thing to do in these cases is to convert them into acids. So these both are bases right now, so convert them into conjugate acids. So remember how to do that is by adding a proton. So this becomes water and this becomes HCl. This is what I do. Okay, I still do this when I'm confused. I will just convert the nucleophile or the leaving group into acid. Now, when I look at water and acid, I know this is a stronger acid. So a stronger acid gives me, remember, a weaker conjugate base. That's it. That's my logic. Okay, so that's how I know that this is going to be a weak base. And then this is the strong base. You can't memorize these things, okay? What you need to understand are the concepts over here. Once you understand how to determine what is a strong base, you're all set. I can throw anything at you or anybody can give you anything and you'll be ready because you know what to look for, okay? So you know, try to understand the concept here, which is that you're deriving this from the acid point of view. All right, because it's hard for us to remember which is a stronger base sometimes. Like, these two, it's fine. Because hydroxide, we all know it's going to be a stronger base. So this was an easy one. But if you can't, convert it into an acid, okay? Now, what did we mean by this? It means also that if I were to give you this reaction and ask you what the product is going to be, and trust me, I will do this, okay? Trust me, because this chapter is all about being able to predict reactions, just like chapter 3 was. So here, if I ask you, okay, what is the product? You are going to write no reaction for this one. Because chloride is not a strong enough base to kick off the hydroxide. And you're going to write that as a reason for me. You're going to tell me that, okay? Because fluoride, not stronger base or nucleophile than hydroxide. You need to write this to understand it, okay? So that's kind of what we're talking about here, okay? So similarly, if I give you something like this, not hydroxide again, this one. If I give you NH2 and then I say, okay, will this reaction happen? And you're like, okay, what do I do here? So the first thing you do is identify your leaving group, okay? So your leaving group is this, which is NH2 minus. Remember, since it's NH2 minus as the leaving group, not just NH2, not NH3, it's NH2 minus. And you're comparing that to hydroxide. So this is supposed to be the leaving group. This is supposed to be your nucleophile. So how do you decide whether the hydroxide is going to be a stronger nucleophile than amide? And you're like, I don't know. So the best thing to do is then again to convert them into acids. So here, this is water. That's the conjugate acid. And then here is ammonia, which is the conjugate acid of amide. So when you look at water and then when you look at ammonia, ammonia is already a base. So if ammonia is already a base, it's going to give you a very strong, this is a very strong base or nucleophile. So if this is a stronger one, and you can say stronger if you want to, stronger base or nucleophile, this reaction ain't happening. It's not going to happen. So you have to be able to predict these things, okay? So take it step by step, process by process, okay? And then determine whatever is a stronger nucleophile, okay? If it's a stronger nucleophile and if it can displace the leaving group, fine, okay? That's good. So that's the only way you can do it sometimes, okay? Not all the times. Now, there are some leaving groups that are really good leaving groups, okay? So good leaving groups are something like SO3 H minus. This is conjugate base of H2SO4, right? So H2SO4 minus 1 hydrogen gives you, and you can write the H first if you want to, if that helps you. There, let me do that. HSO3 minus. So it's the conjugate base of sulfuric acid. Sulfuric acid is a strong, strong acid. So which means the conjugate base is going to be really, really weak. Okay. So which means that now if you had something like this, I'm so sorry, this should be 4 oxygens. One of the oxygen will be connected, and then this is what you have. So now if you wanted to actually just use a halide also, you can, no problem. And you can just write like this if you want to. You don't have to write HSO4 minus. Just write the nucleophile. Make sure that the minus is actually on the oxygen. That will help you a little bit. So this reaction is going to happen because it's a really good leaving group. Okay, so I have to write a couple reactions. So in both cases, I'm using hydroxide. Make sure you write this clearly if you're copying this. Now, if I give you this kind of a reaction, okay, and ask you, is this going to happen? So the first thing you do is you look at this reaction and you identify your leaving group, okay? So generally what happens is that, and what has been happening so far, is your leaving groups have been either halides or any kind of a heteroatom. Heteroatom meaning anything other than carbon and hydrogen. So it has been a heteroatom, so it's been easy to identify. You're like, yeah, I can see that the leaving group is NH2 or OH or Cl. But in this case, you don't really see it. Does it mean it's not there? No, it doesn't mean it's not there. It just means that you have to identify it a little bit differently. So here are 3 hydrogens, but now here are 2 hydrogens. So it means that H minus, and again, remember, H, whatever is leaving, it's a leaving group. That leaving group would be minus. It's not just going to be H. Okay, it's going to be H minus. That's the leaving group. Because remember, the leaving group leaves with its electrons. Okay, so that's why it's always minus. At least in this case. We're going to do some in which they are neutral also, okay, but not right now. Okay, in the bottom one, what's going on? In the bottom one, if you see, I got rid of one of the carbons. So you have 1, 2, 3 carbons. So 1, 2, 3 carbons, and 1 carbon is gone. So which means there were 3 hydrogens here. So it means that my leaving group is CH3 minus. So it's a carbon anion. That's the leaving group. So now the question is this reaction going to happen or not? So which means you have to think about the fact whether these 2 leaving groups that we have here, are they good leaving groups or not? Okay. And how do you determine if something is a good leaving group or not? You look at the base, right? The base strength. And then you decide from there if it is going to be a good leaving group or not. So if you're not able to, it does the same thing again. If you're not able to decide again, if it's going to be a good base or not, you convert it into acids, right? So CH3 minus, and then you convert both of these into conjugate acids. So one is giving you hydrogen, the other one is giving you methane, neither of which is a base. Well, actually, neither of which is actually an acid, I should say, not a base. Neither of them is an acid. We don't consider either of them as an acid. So if both of them are not acids, which means what? It means that their pK is very high. Okay, remember, low pKa means it's a strong acid. High pKa means it's not a good acid. So they have very, very high pKas. So if they're going to be such weak acids, they're going to give a very strong conjugate base. So if they're giving very strong conjugate bases, well, this reaction is not happening. Nope. Nope. Neither of these reaction is going to happen because the leaving groups are not that good. Now, hydroxide cannot kick off the hydride. Okay, H minus is hydride. But if you can find a nucleophile that is stronger than hydride, sure, go for it. No problem. Okay, but just like this, the reaction is not going to happen. Okay, and not because hydride is a strong base. No, because hydroxide is actually weaker than hydride. That's why. Okay, because hydroxide is not strong enough. So this is the case for the leaving groups. Okay, so you have all these different kinds of leaving groups. Later on, I'm going to talk about, when I talk about the exceptions, then I will talk about some other leaving groups also. Okay, right now I'm going to move on to the 4th criteria, which is the solvent. And the solvent I like to keep short and sweet because it's a little bit, it's more practical thing than anything else. So I would like to focus more on what different kinds of solvents there are and just a generalization of how you use them. Okay, so first of all, solvents. You need solvents to do all sorts of reactions. Okay, there are very few reactions that you don't need a solvent, where the substrate itself is the solvent. Okay, and you will do those reactions in the lab. Okay, because in this lab you have SN1 and SN2, okay, in your organic 1 lab. So you're going to do these reactions there. So in some cases, your substrate can be the solvent, but when it cannot be the solvent, or when you need something to dissolve like solids, then you need to have a solvent. So there are 3 kinds of solvents that we talk about. So there is a polar protic solvent. There, leave some space, okay? I'm going to come back. There is the polar aprotic solvent. And then there's the non-polar solvent. So there are 3 kinds of solvents. The polar protic solvent, protic tells you right away that you're dealing with something that has a proton. So this one would be like methanol, ethanol. These are all alcohols, and I'm hoping that you're not having much trouble with the nomenclature because you already know a little bit nomenclature, and methanol, ethanol, eth, and then ending in the ol, okay, which is the alcohol. So ethanol, methanol, water is also protic. And then if you have any kind of acid like carboxylic acids, these are all protic solvents. And why are they protic? Because they all have H plus in them. You can treat them with bases quite easily. So they will all donate a proton. So these are going to be your polar protic solvents. The polar aprotic solvents are polar also, but they don't have the proton, which is good, right? Because, you know, if you're treating something with nucleophiles, then the nucleophiles can be bases also. So your base might end up reacting with the solvent, right? So you got to be careful in these cases. So the polar aprotic solvent is something like this. So CH3 and then S, sorry, not C, CH3S, and then CH3, and there is an oxygen here as well. So this one is dimethyl sulfoxide. I'm going to write 2 for you. Dimethyl sulfoxide. You can find more in the PowerPoint also, okay? So if I miss anything here, you'll find more there. As I said, I don't do too much of solvent. I just need you to recognize them. DMSO. And then the other one is dimethyl formamide, which is an amide. CH3, CH3, or dimethyl. If you don't remember the structure of these, don't worry about them. I need you to remember the name and remember whether they are protic or aprotic, okay? And protic are very easy to remember, right? So the protic solvents that I've given you here, or even if I don't give you, you just look for the acidic proton, okay, in them. And that's how you know that they are going to be polar protic, okay? That's it. So then you have the DMS or DMF, which are polar, but they are aprotic, so they don't have the acidic proton. And then finally, the non-polar, these would be things like hexane, benzene. These are non-polar solvents. So the question is, what do I use? For what? So the answer is the polar protic solvents you use for SN1. There is polarity in there, and for SN1 reaction, you need to stabilize the carbocation. Polar aprotic are used for SN2. Generally, Usually we don't use the non-polar solvents as much. And that's all I need you to know about the solvent, okay? Klein goes a little bit more into detail. I don't want you to get bogged down with all the details. Just remember that polar protic solvents will support SN1 and polar aprotic will support SN2. And now you have even more things to add to your table. Okay, that table that I was telling you, you need to make for SN1, SN2. So carbocation or no carbocation, one transition state, two transition states. Now you have the solvents in there too. Any questions on this? So far, so good. Okay. So at this point, technically speaking, I've introduced the reactions to you. When you write the reactions, very simply, like the ones that you have in the self-study sheets, just make sure that you identify your substrate, that you identify the leaving group, you identify the nucleophile carefully, okay? So here's what we can do, okay? I want to show you just a few more reactions, and then we'll see how much time we have. There are some reactions, that happen, especially with halides. It's really, really weird. Like you can do this reaction, which you think like, really, this reaction? I mean, you're just taking a halide and, putting another halide there, but don't forget, iodide is actually a great nucleophile, okay, because it's bigger in size than chloride, okay? So this one will work pretty nicely, okay? But I want you to just think about a few things here, okay? I want you to understand some things here. So when you look at this reaction, what goes through your mind? Okay, first of all is, okay, I'm doing a substitution. That's one thing that's going through your mind. Second, okay, my iodide is the nucleophile. That's another thing. Chloride is the leaving group. Okay, so I have that. The other things that should be going through your mind is, oh, this is a primary halide. Okay, so that way you're a little bit more in tune with the reactions that are going on. The other thing about this is the iodide itself. Okay, so I want to tell you just a little bit. We write iodide, okay, in there. But I don't want you to be confused if I write NaI, okay? Because if I write sodium iodide, I still mean for the nucleophile to be the iodide. The Na is just a counter ion. It's not going to do anything, okay? So which means sodium is in the product also. Remember, those are called spectator ions. They don't do anything. They just hang around. Okay, so sodium is going to be there, but don't get distracted by the sodium because sodium is not taking part in the reaction. The iodide is taking part, and you will see this. Okay, I give you all sorts of reactions so you get comfortable seeing everything in there. You don't have to write sodium iodide. If I ask you how to do this reaction, and I will ask you, okay, so let's say if I ask you, what nucleophile do I need over here? Okay, you can write NH2 minus and I'll be happy. I'm fine. I'm okay with that. You don't have to write sodium amide. If you write NaNH2, I'm even happier. Okay, but NH2 minus is just fine, okay, for me, because I know that at least you understand what the nucleophile is, okay? So this is the kind of reactions you will get from me, okay, is to do, these one-step reactions. Right now, the other thing you might have to do is compare reactions, okay? So for example, I might ask you, okay, which one is going to proceed faster, okay? Which one is going to go faster? Faster meaning which one is, better supported. So you look at both of the substrates, you're like, okay, both of them are primary halides, so that's not different between them. The only thing different between them is that one is chloride leaving group, the other one is bromide leaving group. So both of them are primary halides, which means we are dealing with something that could be SN2. So then in SN2, you need to have a good leaving group. I mean, you have to have a good leaving group regardless of whether you have SN1 or SN2. Okay, that doesn't matter. So you need to have a good leaving group. Now, which one is a better leaving group, Cl minus or Br minus? So in this case, what you again need to do is convert them into acids, HCl, HBr. HBr is stronger than HCl as an acid. So if HBr is stronger acid, it gives you weaker conjugate base. You can see that I'm doing this all the time, okay? And it will be easier for you to do this, okay? This will also help you with your acids and bases, okay? And once you know the concepts, it's fine, okay? And how is HBr stronger? Remember, it was the size thing, right? Between HBr and HCl. So if HBr is a stronger acid, it gives you the weaker conjugate base. Weaker conjugate base then is bromide, which means that this one is going to be a better leaving group. If this is a better leaving group, that means this reaction is going to go faster. This will go faster. So that is the kind of logic you need to start applying. You need to start looking at the reactions in this kind of a way, okay? So you can talk yourself through one thing or the other, okay? Any questions for this one right now? Okay, so what I would like to do, if you guys don't mind, is I would like to start the exceptions, okay? Because I don't want to leave everything to next class, otherwise it will become so big, okay? Even today is big, okay? But what you've done today, just now, until now, this will help you with your 2 study sheets that you have for the SN1, SN2, the nomenclature I know you can do. And then the quiz thing, I'll talk about that. So Cynthia, what's up?
Could you go over which one would go faster for SN1 again, if you haven't already?
SN1 is the same criteria.
It's the exact same?
It's the same because a leaving group is a leaving group.
Okay.
Okay. Yeah. So if you're comparing it according to the leaving group, then it's the same thing because the leaving group has to be good. Okay. If you are looking from the substrate point of view, then for example, if I have something like this, and then if I have something like this, like I don't want to change 2 things on you, okay? I usually don't do that. So I will change either the substrate or I will change the leaving group. So in the first one, I changed the leaving group. Now, if you're looking at this, you say, oh, the leaving groups are the same. So now it's not about leaving groups, okay? Now, today I saw it, okay? So it's okay, you can put your hand down and just give me a second. So in this case, the faster reaction is nothing to do with the leaving group because both of them are the same. Now, this is more about which mechanism do you want to follow, okay? So which one is going to be a faster one with either SN1 or SN2? And so now you look at, this is a secondary halide and this is a tertiary halide. So tertiary halide will follow more on SN1 and secondary will be more SN2. Even if it is SN1, tertiary is still faster, okay, than secondary. So Side, what was your question?
I just want to clarify because I am getting a little stumped on the like the class, like which reaction would prefer with like a radical. I know that like with SN2s, they prefer a primary carbocation.
I have not talked about radicals at all. Where did you get the radicals from?
The study sheet.
No, it doesn't have any radicals. I don't have you doing any reactions with radicals. The only thing I have you identify, and that was in chapter 6, was to identify a radical. I don't have any radicals in there.
I see it on the study sheet that I printed. I don't know if it's like an error or but it's on
It's
the
not an error. Are you sure it's not like a minus or something? Maybe it's showing up too small. Okay,
I don't know
check
if
that. There should, there's,
double
yeah.
check, but it says it on my number 2 and my number 4. It's listed.
Looking at SN1 or SN2?
On both my study sheets for 7.2 and 7.3, there's a question that asks which reaction would go, like
Yeah,
which substrate would go, and it gives a radical as one of the options. So
it's
that's
not
what
a radical. It's probably a minus sign today. Okay, just look carefully. I
Okay.
cannot give you radicals yet. Yeah, we haven't done radicals yet. All right. Okay. Look carefully. Look carefully.
I see what you mean today. It's a little dot,
It's a
but
little.
I just ignored it.
I think it must be a negative sign. Because I think you guys had the same problem in the chapter 6 study sheet. I was looking at it because some of you wrote it as radical, and I'm like, it's not a radical. This is supposed to be a carbon anion. And I think the negative sign was so small that you all thought it was a radical, but it was not actually. So if you go back and look and see, and you think it's marked wrong, and you're probably thinking, why is it marked wrong? I think that's kind of what happened because and okay, so I'm clearing this right now. Okay, there's no radicals. We're not doing radicals until the end of the semester. Okay, so just get that out. Don't even think about that. Okay. All right, so exceptions, there are going to be some exceptions, okay, when we talk about all these reactions, and that's what makes these reactions challenging. Until what we have done now is not even that challenging, okay? Because really what we were learning about was just the basics, right? The fundamentals of a reaction. How does it work? What does it mean to be SN1, SN2? And then what are the different factors that affect, okay, SN1, SN2? But when we get into the exceptions, okay, that's when the problems really start coming in. And that's when you really have to think that, okay, I can't memorize this. I have to work my way through this one and not just, you know, have an answer just like that. You can't have it, okay? So in the exceptions, we're going to talk about a few different things, okay? So the first thing I'm going to talk about is the substrate, okay, for exception. And let me do one thing here first.